countable. If you look at the job, not the job description, the course description, this is actually something that's described and that's required. And one of the reasons it's required is a subtlety that I don't think students always get, which I try to emphasize, and maybe I've cut out too much of it here for you, is that the reason, well, I think it's the reason that the halting problem is undecidable. It has to do with countable versus uncountable infinities. The point is that there are two different infinities. And Cantor, I don't know when Cantor was. He was about the same time. He was before Gödel, right? So right there in the 40s, mathematicians, Cantor and then Gödel and then Turing, and then we're just messing up mathematics. And Cantor said that there was more than one infinity, and everybody got really upset. And now everybody agrees with him, but they got upset to begin with. So the way it's standardly taught is that the integers can be counted, 1, 2, 3, 4, 5. There I'm counting the integers, while the reals can't be counted. And see, I have so many slides on that topic, and we can go into talking about how the integers can be counted and what listed, what does that mean, and how the reals can't be counted, they can't be listed, and what does that mean. But a term or two ago, I put this purple line here, and I had people only learn, again, this is, I make things up. This is Jeff's definition of countable, which is different than Cantor's definition of countable. And down in these later slides, I prove the equivalence between Jeff's definition and Cantor's definition. And if people want to, we can get into more of that. And if we don't want to, then we can go on to doing other things like randomized algorithms or machine learning or something. All right, well, let's just start with Jeff's definition, because I think it's a good one. All right, so it all has to do with the size of a set. All right, so I haven't looked at these slides for a while. I didn't know we started with Planck's constant, but any Planck's constant is a very, 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 very small length. Like a meter is a length, a foot is a length, but this is a very small length. And we want to know how many objects are there of size Planck's constant that are in the entire universe, right? The universe is of size, I forget the numbers, 10 to the 20, 10 to the 30. A Planck's constant is 10 to the negative 30, right? So how many of them are there? Well, here I'm saying Planck's constant is 10 to the negative 35. The universe is 100 billion light years across. So that's so many meters. And so we can measure it, and how many Planck's lengths is it, the universe across, and then it's a volume, three-dimensional volume. So we have a certain number of these Planck's units in the universe, right? So we might call this infinite, but it's not infinite, it's finite, right? So this is a finite set, and one might actually argue that there are no infinite sets in the universe, right? The universe is, everything is finite. It's only mathematicians that made up integers that are infinite, right? All right, so that's finite. Now, right, so anything bigger than this just doesn't exist in our universe, right? But here, let's talk about some other sets. here, let's talk about the set of all alphas, all strings that are a 0, 1 string and they have length 5, right? How many are there? Well, there's 2 choices for the first bit and 2 for the second and 2 for the third, 2 for the fourth and the fifth, right? So there are 2 to the 5 of them,
32.
right? 2 to the 5 choices of strings. And, right, and that's also constant, right? It's not a big constant, it's a constant, right? Now, let's have a different set. This is the set, again, it's a set of binary strings. But now, each string is going to have it can be arbitrarily long, but finite, right? So that's what's integers. Each integer, you tell me any integer, it could be a billion, billion, billion. It's finite, while the number of integers is infinite, right? So each of these strings is of a finite length, right? But how many strings are there, right? How many strings are there that have a finite length? Well, in some ways, it's 2 to the power of arbitrarily long but finite, right? Because it's 2 times 2 times 2 times 2. And so now, I mean, one way you can say that it's infinite right to begin with. Let's even forget about it being a string of length of zeros and ones. If it's just a string of length zeros, then you have the one of length 1 and 2 and 3 and 4 and 5 and 6, right? So already there are an infinite number of different lengths. So we're going to have an infinite number of different strings here, right? But I like to, one thing that you might know that I stress in all of my courses is how to think abstractly about things. And so what is thinking abstractly means is moving from one representation of something to another representation and being able to move between those representations casually, right? That helps with more abstract thinking, right? So I can think about my set S1 as a countable set of objects, and I don't care what those objects are. Why? Because I can move between representations of them. So one representation is I think about alpha being a binary string, that each binary string is a finite length. Or I could take the binary string and put a little sub2 at the right end of it, and suddenly it becomes an integer in binary, right? You might remember, so that this is, the first is the ones column, then the twos columns, and then the fours column. So we have a 1 in the fours column and a 1 in the ones column, so we get 5, right? So here, this is the mapping between binary strings and integers. So the number, I'm not, the number of binary strings and the number of integers is there's a one-to-one mapping between them, right? So we're going to say that they're effectively the same set of the same size, right? So this can be equal to the set of all integers, right? Right. So there's another way of thinking about S1, and the definition of the word countable is that the integers, the size of the integers, though infinite, we're going to say is countable. And we're going to see what that means. Basically, if I want to count the people on my screen, I would go 1, 2, 3, 4, 5, 6, 7, 8, right? I'm counting them with integers. And so you count with integers, and hence we're going to say the integers are countable. Right, so now there's another interpretation of this binary string, right? Binary strings can be grouped into blocks of 4 bits each, and then those 4 bits, oh no, not 4 bits. Is it 8 bits or 16 bits? What's an ASCII? An ASCII character, there are 256 of them. So 2, 4, 8, 16, 32, 64, 128, 256. 8 bits. 8 bits for an ASCII ASCII, right? So you group them in the 8 blocks, and then you get letters, right? So we can also interpret this binary string as a word, right? And then what we have is we have a set of all finite ASCII strings, right? So this is also a set of the same size. All right, now I'm going to do something really quite amazing, and I've had more complicated proofs of this, but let's think about the rationals, right? What's a rational? 3/4 is a rational, right? It's all fractions. And you might think that the number of rationals is much bigger than the number of integers, right? Because look at integers, you have 1, 2, 3, 4, 5, and those are all also rationals. But rationals, you have a lot more of them. In fact, here's something that's true. You give me any two fixed real numbers on the real number line, and there's a rational in between, right? There's so many rationals, so many fractions, like 3 divided by 4, right? So surely there are more of them. But I'm going to tell you, no, actually the number of rationals is equal to the number of integers. Why? Because I have this set of all ASCII strings, and one thing that I can, and what do I got here? You see it's in brackets, 3 divided by 4. Well, you might think that 3 divided by 4 is a rational, but 3 divided by 4 is also an ASCII string, right? 3 is an ASCII string. Divide is an ASCII string. 4 is an ASCII string. You can, those are all ASCII characters. You can get them. You get an ASCII string, right? And so, and that way you can see we got every rational number has this finite description, right? So X, the set of all rational numbers, is also the same size as the set of all ASCII strings, because ASCII strings are just things like 3 divided by 4, right? In fact, you can say this is smaller because cat is an ASCII string, but cat's not a fraction, right? But every fraction can be written down as 368 divided by, right? It's an ASCII string, right? So again, all these sets can be thought of as the same, right? Are people following this?
Yep, I have a question.
Yeah.
So the description has to be finite, right? Not the set itself for it to be a counter.
Exactly. Let's start at the beginning. Set S1 is definitely infinite because there are an infinite number of lengths. There are an infinite number of integers. But each integer has a finite description. Each of our binary strings has a finite description. Each of our ASCII strings has a finite description. Each fraction, 5/8, has a finite description, right?
I'm sorry, how can it be infinite if it has a finite description?
Well, tell me an integer that's not finite.
Oh, okay.
Right?
Yeah, that makes sense.
They're an infinite. That's the dichotomy here, is that they're an infinite number of integers, but each one of them is finite. Right? So here I'm going to have an infinite number of binary strings, but each string is finite. Now, why do we have an infinite number? Well, just in terms of lengths, right? You have, if we just look at strings of zeros, there are an infinite number of them, right? Because you can have the string of length 0 and the string of length 1 and 2 and 3 and 4 and 5 and 6, right? So there are an infinite number of finite strings of zeros because there are an infinite number of different lengths. Is everybody getting that? Now let's talk about Turing machines, because remember I told you that this relates to the fact that there's not a Turing machine that solves every problem, right? There are uncomputable problems. And why is that? Is because every Turing machine, there's one really important thing about a Turing machine that I've tried to stress. Has anybody noticed it? Is that it has a finite description, right? So my alpha, which is a string of ASCII or a string of binary, can be used to describe anything in English, right? You can use it to describe a Turing machine. So that tells me the set of all Turing machines is also countable. It's also, all of these sets are sort of the same set, right? Set of all strings is the same as the set of all Turing machines. Why? Because each Turing machine has a finite description. Now, you might not say equals. You might say some strings aren't the descriptions of Turing machines, right? And so then we would have a subset of. But well, now we're getting to nuances that I don't want to get into, right? We could do a mapping the other direction. All right, so everybody kind of get that? Those are our countable sets. Now let's go to our uncountable sets, right? And in fact, there's a hierarchy of infinites, and that Cantor described, and the finite ones he numbered 0, and the countable ones he numbered 1, and the reals he numbered 2. So those numbers aren't arbitrary. They line up with Cantor's definitions. All right, so now we're going to have a set of all binary strings, but now the binary strings can have, some of them might be finite, I don't care, but most of them will have infinite descriptions, right? Each binary string is infinitely long. All right? So you see the difference. Be it when we were doing 1, each binary string had a finite length. And now each binary string has an infinite length. All right? So, so what can we use? Again, we want to think about how many are there. And now I can think about it's infinitely long. So I can now describe a real number, right? A real number, right, is not necessarily a fraction. It's pi is a real number, but it's not a fraction, right? There's a proof. In fact, in 1090, I spent 30 seconds proving that square root of 2 was not rational. All right? So square root of 2 is a real number, but it's not a fraction. So they're way more real numbers, right? So how do you describe one? Well, you can describe it by a decimal representation, right? If you were doing it base 10, then it would be 0.38712, right? But since we're doing binary strings, let's continue on in our binary world. And we're just going to take your binary string. We're going to put a decimal place at the beginning of it, and then we're going to do it in binary. So here, the 0.1 is the half place, right? So that 1 there represents a half, right? Because this is the 1s, the 2s, the 4, the 8s. We go the other direction. This is the half column, and then the quarter column, and the 8th column, and the 16th column, right? So this number here is a half plus a 16th plus whatever will come later on, right? Does that make sense? And you know, if you go a half, I choose whether to add a half or not, and then I choose whether to add a quarter or not, and I choose whether to add an 8th or not, and 16th and 32nd. You keep going. You're kind of doing a binary search on what your real number is. right? And if you keep going further and further in, your binary search narrows down to one real number, right? But to get down to that actually real number, you need an infinite description, right? All right, so now that says we have here, it's the set of all real numbers, right? And this set, if we're in the mood to, we can prove is uncountable. We can prove that you can't count them. There's no way to list them all. All right, so here's another way to interpret it. We can think about alpha as a function from the integers 2, 0, 1. All right? Each one of these binary strings, right? We have a binary string of infinite length. And what am I going to do with this binary string of infinite length? I'm going to use it to tell me a function that takes an integer as input, and it's going to output 0, 1. All right, how do we do that? Well, quite simply, I'm going to put little indexes under the binary string, right? Here we have a binary string, 1, 0, 0, 1, 0, da, 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 right? I'm going to count the bits, right? Here, actually, here's the funny thing is when I say each string is of infinite length, it's still of a countable length, right? It's not of an uncountable length, it's a countable length. And so here I'm going to count the bits of the string, right? I'm going to count 0, 1, 2, 3, 4 are the bits of the string. Now, am I ever going to get to all of the bits of this real number? Well, not unless I use all the integers, right? If I just do it as an algorithm, 1, 2, 3, 4, 5, here's something that I think is really cool. If I have an algorithm that goes 1, 2, 3, 4, 5, and it just keeps counting, am I ever going to get to all of the integers? No, right? But what is true is that for any given integer, you will eventually get to it, right? So that's a really subtle point that maybe we'll try to remember to get back to, right? So any number. So here, what's my function now? Well, I want to know if I'm defining a function f, I need to know, well, what for every integer as the input, what the output will be, right? So if the input 0, I need to decide what's the output. Well, I come up to my binary string that's supposed to be describing to my function, and I say, what's the 0th bit of my string? Oh, it's 1, so I'm going to output 1. What's my 1th bit of the string? Oh, it's 0, so f of 1 is going to be 0. F of 2 is going to be 0. F of 3 is going to be 1. Right? Does that make sense? And why does this describe a function from every integer to 0, 1? Well, because you name me any integer, maybe 1,000,000,005. Somewhere there's the 1,000,000,005 bit of this infinitely long string, and I will define f of 1,000,005 to be whatever the 1,000,005 bit is, right? But you might also notice that this function requires an infinite description, right? Because I have to tell you for every integer what the output will be. So the description is going to be infinitely long, right? Are people following this? Right? So here we have the set of all functions whose the input is an integer and the output is a 0, 1, right? And all of these sets are of the same sort of nature. There's sort of, we can set up bijections between them. All right? So now, let's do something harder. Here we were doing an input, a function that took as input an integer and return 0, 1, now I'm going to talk about a function that takes in a finite string and outputs yes or no. All right, what's the difference? Well, what the difference is the input now is going to be a finite string. So let's say it's a finite string of zeros and ones. All right. So here, 1, 0, we know is a finite string of zeros and ones, right? But 1, 0, remember on our last page, we said that 1, 0 thought of in binary is 3, right? Because it's the 1 places, the 2 places. So that's 3. So we come up here to our same place and we say, what's the output of f of 3? Well, f of 3, the output is 1. Well, let's just say, 1, 0. So sorry. 1, 0 is 2. 1, 0 is not 3, it's 2. That's why 1 we're going to interpret as true, and 0 we interpret as false. So here, f of 2 is 0. So f of 2 in binary is going to be no. But f of 3 is 1. So f of 3 in binary is going to be yes. Right? Are people following this? Any questions? In some ways, it's straightforward. In some ways, I'm telling you things that rock mathematics at Rock Cantor, everybody got really, there's some real subtlety here.
I have a
So,
question.
you
Go
go
ahead.
ahead.
Sorry. All right, thank you.
Yeah.
So the example there, when you have that function, right, that where you could go from one set to the other set, and
Yeah.
so if I say, like, if I have that string, and then if I say I want to fetch the character of, like, at the millionth index, right?
Yeah.
So am I supposed to make a function that will get me the character at that millionth index, given
Yeah.
that's what I was trying to.
So you might want to say, well, how do you write one of these infinite things down, right? And you can't, because it takes an infinite amount of space. What I started with by saying how many Planck's constants are there in the universe, what I was trying to emphasize there is that even if you took every Planck's constant little spot in the universe and you assigned it a bit, you still couldn't write down one of these infinite strings if you took the entire universe to do it, right? So infinite strings don't really exist. Now, we said square root of 2 or square root or pi, right? Those are infinite strings, and you can imagine then an algorithm, a Turing machine, for example, that you give it as input a bit I, and it returns to you the ith bit. So in some ways, how would I describe an infinite? If I needed to describe an infinite string, I might describe it by giving you a function, this function f, where the input is an integer I, and the output is the ith bit of your infinite string, right? So, but even then, now you have to say, well, how do I describe my function f? Does it require an infinite description? And that's, in fact, that's the whole point, right? The whole point is that these objects, these infinite strings, don't exist, right? In reality, they don't exist. So we as mathematicians might talk about them, but when we really get practical, let's admit that they don't exist.
Okay, so we're just gonna assume that this function exists. It's just going to map it. We're not going to actually focus on the implementation of the function.
Yes, we're not doing any implementation here.
Okay, thank you.
Right? We're talking, in fact, what we're talking here is how many angels are dancing on the head of a pin.
Okay,
Right? You might know that's a classic Aquinas Christian thing, right? Well, I don't know. We don't have, I mean, there might exist angels, but not that I can count on the head of my pen. Right? So that's what we're talking about here. Right?
So if I was to interpret this, so with countable infinite or infinity, each element, although it have an infinite number of elements, we could count each element.
Yes.
But for the uncountable infinity, since each element is of infinite length, we'll be stuck on one element. So technically, we can't count each element, right? So
exactly.
Is that how it's interpreted? Okay.
Exactly. All right. So now,
Professor.
Yeah.
Sorry, just to further clarify. So we say a set is uncountable if there exists just one element that's infinite.
No, because that would be silly. Because if I had a set that only contained one element in it, even if it had an infinite description, it would still only have one guy in it, right?
Yeah. So then, would every member in the set need to be infinite?
So that's the thing is, we're gonna get it. I mean, kind of what we're saying here already is that different numbers have different descriptions. Right?
Yeah.
So, right, 1/3, it has a description that is 0.333333 that goes on forever, right?
Yes.
So 1/3, you could say, has an infinite description. Yeah, but 1/3 also has a finite description, right? It's also...
So it depends on how you represent the description, I guess?
Yeah, we have different descriptions. So pi, for example, or square root of 2, they have infinite descriptions, right? They go, right? But they also have finite descriptions. Tell me a finite description for pi.
The symbol pi.
Brilliant. Brilliant. Exactly. Students usually have a hard time with that question. Sometimes if you ask questions that are too easy, then people have a hard time. Right?
Okay, so in this case here, we're looking at a description and we're seeing if there are some infinite members in the set.
Well, I can't point at any one member and say it needs to be infinite, right? You could choose any string in this set and I could call it Bob, right? Then that string would have a finite description, right? His name would be Bob. But that's why Cantor doesn't do what I'm doing here. Cantor has a much more formal definition because different things can have different descriptions, and so I'm not being as formal here, right? I'm talking about different examples, but now when we have a new set, do we have to say? So I guess what my point, we're going to get into this later, but what I'm saying is a set is uncountable. A set is countable, right? We can define, it's hard to define uncountable. It's easier to define countable. It's countable if you can count it. You can count it if you can map each one of them to an integer, 1, 2, 3, 4, 5. You're counting it, right? It's countable if you can assign to each one a unique finite description. Right?
So if given a question on a test, would it be more appropriate then to do some sort of reductions to show it goes to some known uncountable set or some known countable set?
So there is going to be a test question on this tomorrow, and if you're trying to do the reason I'm doing this way is if you were trying to do a mapping, a bijection between one set and another set, then you might have a hard time. And we could get into lots of slides on how to set up these bijections. And so I'm trying to have a different thing. Could you imagine a way of describing an object? If you have a set and there's a way to give a name to every object where each object has a finite name,
Mhm.
then it's a countable set. That's what I'm saying. And
Okay.
if you can't give everything a finite name,
Mhm.
then it's uncountable.
I see. So in this case here, if alpha is strings of zeros and ones of infinite length,
Yeah.
since we don't know where it ends, we can't give it a name. That would be
Yeah,
unique.
we can't give each of them a name.
Yeah.
I could call some of them Bob, one of them Bob, and one of them I could call a Harriet, but I
Yeah.
can't, there are too many of them for me to give each of them a name.
Okay. Gotcha.
All
I
right?
think that makes sense. Thank you.
Excellent. All right, so let's go through our examples here, right? So here we talked about the number of functions that go from binary strings to yes, no. Well, what is that? That's a computational problem. Remember the way we talk about languages in 2001, it's the set of binaries. Each language is, what is this language? Is you, for every binary string, you tell me whether or not the string is a yes input.
Sorry, could you, I think you might be going over it later, but could you go over some examples of this? Because I don't know why I can't wrap my head around it for some reason.
Aren't these all examples? Did
Oh.
you get going from a binary string to a function?
Yeah.
And to a language?
Yeah.
Right?
It's just a little
I'm
bit
just saying,
confusing.
if you give me an infinite binary string, I can use it to describe a function from integers to 0, 1. I can use it to describe a language. What is a language? Language is from every binary string, I tell you whether or not the string is in the language. So for example, English. English is a language, right? So what is a language? What is English? In some ways, English is a function that takes an ASCII string as input and outputs whether or not it's a proper English word, right? Cat, it's a proper English word. DDD is not an English word. It's not in the dictionary, right? So a language is a mapping from these finite strings to yes or no, it's in the language, right? So each language has an infinite description, right? If I wanted to tell you a language, I would have to tell you for every finite binary string, every possible input, I would have to tell you whether the answer is yes or no, right? So the set of all languages is uncomputable. Set of all languages is uncountable. What about the set of computational problems? Well, a language is just a computational problem, right? The input, it's more complex in some sense. What a computational problem is you give me what do you need for a computational problem? For every possible input, like sorting, is for every possible string of integers that you give me, the required output is those same numbers sorted, right? So that's a function from inputs to output, right? And sorting is a pretty easy one because I have a really quick description for describing the sorting problem. I just tell you, you give me a bunch of integers, the required answer is those same integers sorted. That's a finite description of sorting, right? But a random computational problem, if I wanted to tell you a randomly chosen computational problem, I would have to tell you for every possible input what the required output would be. right? So the number of computational problems is uncountable, all right? So here's just a chart here. We have the length, we have finite integers in reals, right? So if the length of every string is 5, then the number of strings is 2 to the 5, and those are both finite. If it's an integer, then the length of each description is finite, but we have a countable number of them. And I like to think about it as a random real. Suppose I gave you a truly randomly chosen real. Try to even think about that means. A truly random real where it has an infinite number of bits, and each of the bits is randomly chosen, right? Then do I have a finite description for it? No, every bit was chosen randomly. How can I? It's like compression. How could I take, here's a question. If I give you a random file of length 1 billion, right? It's on your computer. It's 1 billion bits that I chose randomly, right? Can I compress that? Can I compress it to a file smaller than 1 billion? No. No, you can't, because every bit sort of matters, right? Why can I compress a photograph? Well, because there's a lot of redundant information. There's lots of big stretches here on the wall back there, big stretches of purple that you can describe by a shorter description, right? So it's all about information theory. If I gave you a random string of bits, it's not compressible. So it doesn't have a finite description, and so there are an uncountable number of them.
Sorry, could you go back to the last slide they were on just now? Thank you. I have a question. No, the one with the table. I'm kind of confused because with the countably infinite, because 2 raised to the power of 5 is 32.
Yep.
Sorry. Is it 32? Okay, yeah.
4, 8, 16, 32, yes.
32, but it's like, if you can tell it's 32, it's
finite,
but it's
that's why it says finite here.
It says countably infinite.
No, here the column here goes across this row. See, this row here is what's finite. The length, finite sets. Each object has a length bounded by 5, and so the number of them is 2 to the 5. Those sets are all finite. Well, the integers, each object has a length that's finite but arbitrarily long. So here, I guess the 5 is supposed to mean not only is it finite, but it's constant. It's bounded by a fixed number, right?
Right.
So it's finite. They're 2 to the 5 strings of length 5, because that's all. This here, 5 is a constant, and 2 to the 5 is finite. Now, integers, each one has a finite length, but there are an infinite number of them, but you can count them. While the reals, each one has a random one at least, has an infinite length. And so there are an uncountable number of them.
Oh, okay. Thank you.
Right. So I'm just saying the same things again, right? Because I've made slides on I've been teaching this for 20 years, so I have slides from different decades, right? How many integers are there? Each of them has a finite description. How many fractions are there? Each of them has a finite description. So the number of them is the same. Each real, a random real, here I didn't say every real requires an infinite description, because pi has a finite description. So does the square root of 2. But a random real requires an infinite description, right? So there are way more reals. The set of Turing machines, each Turing machine has a finite description. Each Java program has a finite description. So the number of algorithms, the number of Turing machines, well, each of them has a finite description, so the number of them is countable. The number of computational problems, right? Each of them, a random computational problem, requires an infinite description. Why? Because for every input, I need to tell you what the required output is, right? So a random one requires an infinite description. So the number of computational problems is uncountable. The set of all computational problems is uncountable, right? And so there are way more computational problems than there are algorithms. Just way, way, way more, right? And so when we prove that there are computational problems, so what does that tell us? That tells us that most, I'm not only saying that there exists a computational problem that doesn't have an algorithm. I'm saying more than that. You take a random computational problem, it's going to require an infinite description. And hence, it won't have a finite. What is an algorithm? An algorithm is a finite description of a computational problem. So here's a question. The set of computational problems that are computable, is that countable or uncountable? The set of computational problems that have an algorithm, well, each of them has a finite description. Why? Because the algorithm that computes them is a finite description. So the set of countable problems, the set of computable computational problems is countable. But the set of computational problems is uncountable. So there are way, way, way more computational problems than there are computable problems. And so the reason remember our proof that there exists the proof that there was a hard problem looked too easy. And the reason it was so easy is because it's just so true. You know, every random computational problem is uncomputable. So that's why there exists problems such that for every Turing machine, it fails to compute.
Because
and that's
in this
that set of slides.
because when you say random, like computable or random number, we're expecting like the worst possible, as if the adversary would give us it, right?
Yeah.
We're expecting like the worst possible case.
Yeah, or
computable.
Or if I wanted a random computational problem, how would I do it? For every time somebody asks, what's the input? For this input, what's the required answer? I would flip a coin. For this input, there's a random answer. For this input, there's a random answer. For this input, there's a random answer. How many times do I have to flip a coin to get my computational problem? Well, there are an infinite number of possible inputs. So I have to flip my coin an infinite number of times. So it requires an infinite number of bits to describe it, right? In fact, I would almost say that if you can also say, if you have a set and you wanted to randomly select one, how many times you have to flip a coin. And if you only have to flip a coin a finite number of times to select it, then in some ways it has a finite description, right? The description is the coin flips. But if I have to flip a coin an infinite number of times to get one, then it has an infinite description, it needs an infinite description, right? Everybody buying this? So if you flip through here quickly, there's all these mappings, right? How to do mappings. Here's this crazy mapping from fractions to integers, right? One thing that's cool, here's all the fractions, right? Here's 4 divided by 3 and 6 divided by 5, right? So how would I count them? Well, if I count them 1, 2, that way, if I count them that way, am I going to get to them all? I go 1, 2, 1 over 2, 1 over 3, 1 over 4, 1 over 5. I'm counting fractions. See, I'm never gonna get to 3/4. So that's a bad counting, right? But if I count this way along the diagonals, then I'll get to them all, right? So there are different ways of counting, and that's the way Cantor did it. But for me, I like to do it by these finite descriptions, right? So here is a something that I think is cool. In fact, gold star this, because I'm thinking about putting a question that has to do with this page on either this test or next test. Okay? Suppose I wanted to write an algorithm that iterates through every tuple, A, B, and C, right? A is an integer, B is an integer, C is an integer. I want to flip through all of them, right? And if my code, I don't know if previous slide, here's one code, right? Loop over all values of A, and then loop over all values of B and loop over all values of C. Is this going to print all the tuples A, B's, and C's? No, because we're going to start with A being 0, B being 0, and then we're going to loop through all the C's, right? We're all going to get 0, 0, 1, 0, 0, 2, 0, 0, 3. We're never going to get A being 1 or 2, right? So this is a bad program, right? People follow that? But what about this next program? Here I'm kind of doing the diagonals. What I'm going to first do is, well, A and B and C are all finite numbers. So I can compute the sum of them. What's A plus B plus C, right? And now I'm going to loop over what's the sum of A, B, and C. Well, then what I'm going to do is I'm going to loop over all values of A. Well, I know the sum already, right? This is kind of my first order logic thing, right? I have a current value of sum, right? For any current value of sum, that value of sum is finite. So when I loop over the A's, I know my A is, all the numbers are positive, right? So I know my A is at most sum. So I don't have to have an infinite loop. This loop can be finite. I loop from 0 to sum. And my B is also finite, right? I don't have to go all the way up to sum because I know my A is eating up some of my sum. And then I don't have to loop over C at all, because once I know A and I know B, I can compute what C is, right? And what I claim is that this program will never print the same A, B, and C twice. And, well, it will never print all of them, right? Though this, here what we write here is, though this will never list them all, each tuple, A, B, and C, will eventually get listed, right? Why? Consider some tuple. A 3, 7, 5. That's some tuple, right? I'm going to prove to you that it gets printed. Why? Because what's the sum? Add it up. 3, 7, 5 adds up to 15, right? So when sum gets to be 15, then when A gets to be 3, and when B gets to be 7, then C will be computed to be 5, and we will print 3, 7, 5. Right? Does that make sense? right? So this is a way of what we call counting or listing all these tuples, right? I want to say the set of all triples, A, B, and C, is countable. Why? Because here I'm more or less counting them. I'm listing them, right? Here, a set is countable if there exists a list. Here's a list. There exists a list such that every object in the list, there exists a place, an index in the list where that object appears, right? So here's my set. It may be infinitely big, but I can come up with a countum. I could go count 1, count 2, count 3. And so now the chair appears in the list at 3, right? The object 4, it appears in the list at index 5, right? That's why this set is countable, right? But if we come over here, oh, here's what I was also saying. How can I count these things? Well, I give each one a finite description, right? And once it has a finite description, I can turn the finite description into an ASCII string. And then I turn the ASCII string into an integer. And so now I've given every object, I've counted them, right? I've assigned every object an integer, right? And here, fractions, right? This fraction 2/3 has the description 2 divided by 3. So it has a finite description, right? So now let's go on further. What was? Let's do here. This page right here. All right. I'm going to do this really fast, but that's just so that you have a feel that it exists. All right. If you want to dive into this because it's really cool, dive into it. But I want you to have a feel that this is a proof. I want to prove to you that the reals are not countable. So this is what Cantor did. He said if they were countable, then there would be a list. You could list them all. And I want to prove that you can't list them all. All right. So I have my adversary here. What we want to say, if it was countable, they would exist the list. But we want to say, no, there doesn't exist a list. Why? Because for every list, there exists some object in your list that hasn't been counted, right? Remember when we're saying countable, where's countable? Is for every list there, a set S is countable if there exists a list. And what is a list? A list is a way of assigning every object an integer. It's a way of assigning every object a finite description, right? So we say a list is countable if there's a way of giving each object a finite description. You give it an integer, you list it, such that every object that's in your set is counted. Why is it counted? Well, because you give me an object that's in the set, I can tell you where it is in my list. There exists an integer that's in my list, and sure enough, I've listed. Oh, that's I switched from this one to this one, right? This is saying it is countable, right? Because there is a list such that for every object in my list, there's an integer that object is listed at that spot, right? So how do we say it's not countable? So you see how this is all first order logic, right? This is all 1090 stuff, right? How do we know that for every list, if it's not countable, then we just take the negation of this, right? Exists turns to for all turns to exist, equals turns to not equals. Says it's not countable if every list, there's an object that you haven't listed, all right? So let's come over to the proof. We're trying to prove for every list. So let the adversary give me an arbitrary list of the reals. Here, what I have here is an arbitrary list of the reals. What did I list first? Well, 12.343, da da da. That's a real number. What did I list second? Some real number, right? Here is a list. It's listing all the real numbers. Did I include them all on the page? No, because it's an infinite list, right? We have an infinite number of integers. It's an infinite number of lists, an infinite number of reals. But I'm claiming that this object here is a list of all the reals, right? So what I have to do is the adversary gave me a list, right? And I need to, right? So here's my list. My goal is exists an X. My goal is to come up with a real number that's not in your list. All right? You're my adversary. You gave me this list. You said I counted all these reals. Excellent. I'm going to come up with a real number that's not in your list. All right? How am I going to do it? Well, it's called the diagonalization proof. And when we prove that the Turing machines can't compute the halting problem, right? We had the Turing machine take the Turing machine as an input. And that was basically a diagonal. So that was also a diagonalization proof, right? And so now what I'm taking, here is the diagonal, right? I'm taking the first digit of the first number and the second digit of the second number and the third digit of the third number and the fourth digit of the fourth number, right? That's a diagonal. And what I'm going to do is I'm going to form a new number. What I'm going to do is I'm going to take each of these digits, I'm going to 3, and I'm going to add 1 to it, and I get 4. I have 0, I add 1 to it, and I get 1. I get 9, I add 1 to it. Oh, let's cycle around to 0 again, right? And what do I get? I get the number 4104, right? Here, I took the diagonal and I added 1 to each of those digits. Everybody see that? And that's just like we did in the proof of the halting problem, right? We took the diagonal and we changed the diagonal, right? The diagonal was, what does M do on M, right? Well, this is different than what M does on M. Our hard problem that is uncomputable, our hard real number that's not listed is different than the diagonal, right? We take the diagonal and you change it. And that, right? So here it is just, right? 3 is changed to 4, 0 is changed to 1, 9 is changed to 0, 9 to 0, and so forth, right? You gave me a list of all reals. You give me a list of all Turing machines. I will find a computational problem that was not computed by your list of Turing machines, right? I'm going to find you a real number that's not listed in your list of real numbers, all right? Here's my real number. It's the diagonal changed, all right? So now I want to prove that this real number is not in your list. How do I prove it's not in your list? Well, let's continue on. It says for all I. Well, the adversary gives me an arbitrary I. Let I be an arbitrary integer. N, it stands for natural number integer, right? Positive integer. And I'm going to show you that the list, the real number, that location I is not the number I created. I'm going to show you that this real number that I created is not in the list. Why? Because you give me some I, and I will show you that it's not at the ith location, right? Why is it not? How is this different from the guy in the ith location? Well, this number and the number that's in the ith location, I know differ in the ith bit, right? I don't have to study the whole ith number to know that it's different. Because the way I construct it is that my real number is different than your ith number in the ith bit. So this real number appears nowhere in nowhere in your list. And the reason I can do this is because the real number that I'm writing down has an infinite length, right? I need to change I need to come up with a real number that's different than your first number, and it has to be different than your second number, has to be different than your third number, but I have an infinite number of things that I can change. So I can change it so it's different than your first and your second and your third and your fourth, right? So it's the fact that this real number is infinitely long that allows me to come up with a real number not in your list. And that's the entire proof. That's the entire proof. Here it is written down before I had PowerPoint, and that's it. That's it. People kind of get this?
I have a question about that. Could you mind going back to that slide again? Yeah, so if we take the diagonals, right, do we have to prove that the diagonal number that you made isn't the same as, like, so if you made it from the ith thing, right, like, if just you saying that this number is infinite, that's pretty much all you need to say, right? That's the Turing machine.
I have to prove to you that it is a real number, right? Why is it a real number? Well, because it's the concatenation of an infinite number of digits between 0 and 9. That makes it a real number, right? And it's not in your list. How do I know it's not in your list? Well, it's different than the ith number in the ith location. So it's not in your list, and it is a real number. Hence, you did not list all the real numbers. Hence, the set of real numbers is uncountable. And why are they uncountable? It's because they have these infinite descriptions, right? It was the infinite description that allowed me to do the diagonalization.
Otherwise, you'll probably get some duplicates, right? If it wasn't,
yeah, exactly. If we were only talking about finite things here, then I wouldn't be able to change it. All right? I mean, finite things do can be counted, can be listed.
Gotcha. Thank you.
Right? It is really fun things, right? And you should have some appreciation for the ugly nuances of computer science if you're going to be in computer science. And are you ever going to use it? No, but it's just as interesting as studying any other weird thing.
Hash tables and stuff?
What?
Don't you use this in hash tables and stuff so you don't get any overlap?
It's certainly, the concepts come up, right?
Yeah, it's just implicit, but yeah.
You know, the idea of compression, the idea of information comes up, the idea of different representations of different things comes up. The fact that, in fact, the fact in computer science, I can represent an integer as long as it's not too big, but I can't represent a real number, right? Because it has an infinite description, right?
Gotcha.